hate it, but yeah. So, my name is Pedram Ghamisi, and it's lovely to be among you, you fantastic researchers, you rising stars. I believe by the end of the day I can learn a lot from every and each of you. Well, the title of this talk is AI for Earth Observation, Prioritizing Responsible AI Practices. AI for Earth Observation. It sounds like an interdisciplinary work. Well, AI is existing in the remote sensing community for quite some time. Yeah. It can be traced back to almost 40 years ago with some pioneering works by David Landgraf on high dimensional data. But why AI for EO now is a hype? It's, in my opinion, has been revolutionized since a couple of years ago because people finally understood, both domain experts and AI experts finally understood, if they really want to do something out of the box, they need to engage in interdisciplinary work. And of course, some initiatives, some goals like sustainable development goals has speed up this process as well. Well, in this presentation, I'm going to talk about a few examples in which AI for EO plays an important role, but I would like to look at them from the perspective of responsible AI. Well, Sylvia, you already mentioned that. Since 2018, I'm a group leader and research professor at Helmholtz, and I'm a visiting professor at Lancaster University, and until very recently, I was a senior PI at the Institute of Advanced Research in Artificial Intelligence, leading the AI for Remote Sensing group. We are working on a variety of subjects, including trustworthy, explainable, and secure AI, AI for social good, foundation models, weakly supervised learning, multimodal and multi-temporal fusion, for example, as an example, vision language models, and high-dimensional data analysis like hyperspectral data. But with a particular focus on open science and benchmarking, and with that, we hope that we can bridge between industry and academia by disclosing more and more benchmark data sets and software platforms. Well, as I said, I'm going to present a couple of examples in which AI for EO plays an important role. But of course, behind these examples, there are a multitude of fantastic people, fantastic researchers, students, and research scientists. And actually, they are the main brain. I'm simply here to report the great job that they are conducting. Well, let me start my presentation with these statements. Many of the concepts discussed here may have exceptions. Actually, this is the case for everything related to AI. You already have exceptions, or you will see some exceptions in the near future. So in these cases, I'm either sharing my personal opinion or speaking from a general perspective. Well, this figure shows the number of papers dedicated to AI for Earth observation from 2014 to 2023 on the subject of AI for EO, published by key journals in the remote sensing community, like Remote Sensing of Environment, ISPRS, JSRs, Letters, and TGARS. As you can see, the number of papers dedicated to AI for EO has been exponentially increased. But in my opinion, there is something that we should have a closer look to. Before being lost in the beauty of AI, we should define some good practices, some ethical rules to lead our AI for EO works in the best way possible. And this is hopefully what we can do today in this session and the next session. Well, what is responsible AI? Let me read it out from here. Responsible AI involves developing and using AI systems in a manner that prioritizes ethical considerations, societal well-being, and the mitigation of potential risks. Very recently, we wrote a paper on that, Responsible AI for Earth Observation, in which some of the lecturers are also participated, fantastic researchers from all over the world. And you can see, for example, Fabio is there. Claudio is also there, Weikang is also there. So in this paper you can find quite a lot of information about different ethical aspects of remote sensing and AI for Earth observation. But as I said before, we are not going to go through all the things written in this paper. Simply we are going to provide a couple of examples for each of those building blocks, and we are going to take a look at them from the AI responsible practices. Well, in our paper, we divided responsible AI into a couple of parts, including social good, geo-privacy, ethical concerns, AI security, and mitigating biases. Well, one of the co-authors said a very nice thing about this figure. When you work with optimization approaches, you always have an objective or fidelity term, and you also define some constraints to lead your optimization goal in the best way possible. Here, social good is the final objective, but other materials like geo-privacy, ethical concerns, AI security, and mitigating biases or mitigating unfair biases are the constraints which should be considered here. Well, this figure shows the history of AI in terms of data and model-centric approaches. There are quite a lot of information here, but I'll only mention the most important parts. The blue parts simply show the history, and the orange part reflects my own opinion about presence and the future of AI for Earth observation. As you can see, our community, our scientific community has bounced between model-centric approaches and data-centric approaches for quite some time. But eventually we got to a point that I think we are done with either model-centric approaches or data-centric approaches. We are in the era that we need to bring together advances in both AI or models and data together in order to solve real-world scenarios like climate change and so on. So we passed the era of either data-centric approaches or model-centric approaches, and we started the era of data model-centric approaches. And the hype of foundation models, in my opinion, would be a good evidence for that, because for foundation models, you need to bring advances in both AI and data together. You develop something, a sophisticated network, and you train it on millions of images. And hopefully with that you can handle a variety of applications. Well, the history of responsible AI has been intertwined with the history of AI as well. It was in late 2010s or early 2020s that a few concepts like AI biases, fairness, transparency, and accountability began to receive increased attention. Well, same as the history of AI, responsible AI concerns both data and model. It considers the whole chain from the beginning to the end, from data collection to model development and even interpretation of the results that you get from your AI approaches. Well, by the way, one postscript here. I mentioned 1950s as the birth of AI, but AI can be traced back to much earlier than 1950s. Here, by birth of AI, I meant a workshop on the distinct topic of AI, which was attributed to a workshop in 1956. Well, let me start the first example. I call it resource-efficient AI development using weak supervision, and the scientific part is taken from this paper, which was published in IEEE Transactions on Image Processing. Well, one of the key issues that we have in the remote sensing community, something that we are struggling with for quite some time, is a lack of labeled data. You know that better than me. Because the collection of labeled data is either expensive or time consuming, and sometimes dangerous, because you need to organize field campaigns in remote and complex areas. And this is the main reason why most of the time we have only a limited number of samples to deal with. But if you really want to use that as the input to your deep learning approaches, data-hungry approaches, they will simply collapse because of some biases like overfitting. And overfitting occurs when there is no balance between the number of labeled data and the number of trainable parameters that you have in your deep network. Well, in order to address that, the community stepped toward unsupervised learning in the first step. Well, unsupervised learning is really good. So you have a bunch of data, you develop a method, and you perform that on the data set that you have, and you get some results. But there was an issue here for remote sensing related tasks. When you perform unsupervised approaches on remote sensing data, you come up with a mess. 1,000 clusters with no physical meaning. And after that, you need to spend quite a lot of time to interpret each of those clusters and give them some sort of meaning. And actually, well, it's unsupervised, but at the same time, we spent quite a lot of time on that. So it's even more time consuming than supervised approaches. This is why unsupervised learning for many applications is not a hype at the moment. And the community started to step towards some other techniques like weakly supervised approaches or self-supervised approaches. The work that I'm going to present here is a consistency regularized region growing network for semantic segmentation of urban scenes with point level annotations, which can be categorized as weakly supervised approaches. It was in until 2020, the general mindset in the remote sensing community was that without having high quality labels, it's impossible to produce high quality maps. Or if you use low quality labels, the outcome would be low quality maps, or the concept of garbage in, garbage out. But back then, we had a different opinion. We organized 2 contests in 2020 and 2021 through IEEE, IADF Technical Committee, together with a number of colleagues from DLR, Weikang, Helmholtz, Microsoft, Technical University of Munich, and under the umbrella of IADF and GRSS. And the idea was to disclose multi-sensor data together with lots of low-quality labels, as you can see here, for example. And the outcome was to produce high-quality maps using low-quality labels. Well, I think this accelerated the existence of weakly supervised approaches in the remote sensing community. And since then, weakly supervised approaches have been developed in different ways. The first way, as I mentioned before, using low-quality labels to produce high-quality maps. The other one is to use point-level annotations instead of dense annotations as the input to your networks. And of course, when you go for point-level annotations, you can save quite a lot of time because you don't need to annotate, for example, boundaries between different classes or different objects of interest. And the other one is using class priors, which is very much relevant to the social good as well. For example, we pointed out it's not that difficult to find some information through censuses or through governmental information or so on different applications. For example, let's imagine that you want to perform classification on a rural area, and all you have are some weak information about the class distribution, different types of crops harvested in that area. For example, 30% crop A, 20% crop B, 30% crop C, and so on. So here you can lead your self-supervised approaches in a weakly supervised manner without having any labels, only class proportions to produce high quality maps. Well, you can find quite a lot of information about it here. We validated this class proportion for a variety of applications like crop monitoring, different species of tree classification in forested areas, and so on. But anyway, so there are different ways to consider weakly supervised approaches, but here I only focus on one example related to point level annotations. Well, what is semantic segmentation? Semantic segmentation is a fancy name for pixel-wise classification. Semantic segmentation is used in computer vision. Pixel-wise classification is used in remote sensing, but they are identical. So in semantic segmentation, you give a label to each pixel, and each of those labels or colors represent one particular class. Of course, when it comes to semantic segmentations, deep networks are among the state of the arts. But there is one issue here. They have quite a lot of trainable parameters, and usually they require a lot of training samples to be trained in a proper way. So if you use only a limited number of training samples here, your deep learning based approaches will collapse. So the challenge here is the task of creating dense annotations, which is really time consuming. For example, it was reported that for one image in the Cityscape benchmark dataset, you require almost 90 minutes of time to fully annotate the image. And you have more than 25,000 images in that database. So you can see how time consuming this process would be. So here we want to develop weakly supervised approaches to achieve accurate results with reduced efforts. Well, as I said before, when it comes to point level annotations, instead of dense annotations, you can save a lot of time. So because you simply put a dot on each object, on some of the objects, and you use them as a training samples. You don't spend any time on fully annotate, for example, different objects or the boundaries between different objects of interest, which would be really, really time consuming. In order to do so, maybe we can use this simple inspiration. Actually, this is not a new thing. This simple inspiration shaped the backbone of spectral and spatial classification in the hyperspectral domain. Simply, we can expand the number of label data that we have through some simple rules, like 8 connectivity rule and so on. So what we want to do here is that the inspiration is that adjacent pixel in very high resolution images most probably belong to the same class of interest as the central pixel. So maybe we can expand the number of training samples that we have in our deep networks in an automatic way. To do so, we developed this approach, which is composed of one backbone layer and 2 classification heads, the base classifier and the expanded classifier. So the backbone can be replaced by any other networks. Here we use VGG, but it can be replaced by ResNet or something. So you take the input image, you pass it through the backbone network, and you perform the base classifier, or FV. And you estimate the loss. Here you use segmentation loss, which is based on cross entropy loss function. And you use point level annotations as the input to that. And with that, you can estimate the class logits. After that, you can perform class expansion using 8 connectivity rules. Here, you take a look at the neighboring pixels, and if they belong to the same class of interests with high probability, and the probability comes from the output of the base classifier or class logits. If they belong to the same class of interest, you perform expansion. And you continue this iteration by iteration until no other pixel can fulfill this criteria. And then, as the output, you can have the expanded annotations, which would be used to estimate the loss for the expanded classifier. Well, we are going through pseudo labels to address one of the annoying biases existing in deep learning, overfitting. But pseudo labels itself can produce some other types of biases. So we want to avoid them as well. So one of the issues that we have here through 8 connectivity rules, and when we want to produce pseudo labels, most of the time big classes, we produce more samples for big classes, and the small classes will vanish out. And most of the time in the remote sensing community, those small classes are of importance, not those big classes. So the loss function that we develop here should be capable of handling imbalanced samples. For that, our loss function is based on low-loss softmax loss, which is based on, so it optimizes intersections over unions. It works with that, and with that, it can emphasize on both small and big classes at the same time. So why we use, for example, cross entropy loss function for the base classifier, and why we use low-loss softmax for the expanded part, maybe it's your homework. They have their own advantages and disadvantages. They cannot be used everywhere. What? Anyway, so with this, we can address the class imbalances, which is another type of bias to some extent. There is also another thing here. As I said, we have 2 streams here, the base classifier and the expanded classifier. Each of those has its own advantages. The base classifier uses only very few samples, but the quality of those samples are high. For the expanded part, we use quite a lot of samples, but we would have, most probably will have noisy samples there as well, because the output of region growing, although it expands the classes, it also produces noisy labels. To address these bias, we need to let these 2 algorithms, these 2 streams learn from each other, and we will do that through consistency loss that we proposed here. Here, these 2 will learn from each other, one with a lot of samples, but noisy samples as well, one with a limited number of samples, but those samples are of high quality. And the final loss is the average summation of these 3 losses: the segmentation loss, consistency loss, and expansion loss. But let me provide you with some results here. We've validated this approach on 2 benchmark datasets, Weikang dataset and Zurich summer dataset. And here you can see the number of annotations that we have. For the pixel-wise annotations, you can see the numbers, but we use the point level annotations, but we didn't choose anything at random. Those samples are also benchmarked in the community. And you can see that there are much fewer than pixel-wise annotations. Well, and here are the results. It looks a bit complicated. There are many numbers, but I'll walk you through that. In the first column, you'll see different approaches, mostly weakly supervised approaches. And the last one is Oracle, or the result of a fully supervised approach. What we want to do here is to use only a limited number of training samples, but get good results, as good as Oracle, which uses all the samples at the same time. Okay, for the case of Zurich summer datasets, you can see that the proposed approach can outperform other approaches in terms of mean F1 score. Let's skip all those intermediate numbers, class-specific accuracies, and focus on mean F1 score. And well, the approach can outperform other approaches, and the result that we get for Zurich summer dataset is very much close to the result of Oracle. This is the objective that we had. We want to use only a few samples, but at the same time, we want to get the result of a fully supervised approaches. But when it comes to Weikang dataset, of course, we can, well, based on those numbers, the results are better than other fully supervised approaches. But there is still a wide gap between the result of the proposed method and the result of Oracle, 10 percentage points. Why? Why this happened here? The main reason for that is that when we use pseudo labels, of course, we can expand the number of labels that we have. Yeah. Well, we can increase the number of samples that we have using pseudo labels, and it helps us to increase the generalization capability and scalability of the approach. But through that, we are producing some noisy labels as well. And those noisy labels will avoid us, in some cases, to reach the result of a fully supervised approaches. Well, the considerations, if I want to summarize everything in 2-3 sentences, well, producing pseudo labels is a great way for weakly supervised approaches to mitigate overfitting, one inductive bias, and this is one of the key factors of responsible AI. And it can expand the data set, and it can improve the generalization capability. But at the same time, we should be careful about the use of pseudo labels because it can introduce some other biases. So, of course, in one paper, you cannot solve all the issues existing in the world. But I think the best step forward is to be transparent. So if you develop something, of course, you are mitigating a lot of biases, but at the same time, if you are aware of some inductive biases, you should report that clearly in your research work as well. And here you can find all the things related to this work, including codes and stuff. So this is the first example. After each example, we can have some Q&A if you want. So when it comes to applications in remote sensing, the first step is data collection, right? And it's quite common nowadays to use our own UAVs to capture data. When it comes to remote areas like this, most of the time we don't have any issues. But when it comes to some areas like urban areas and urban-related applications, we cannot easily use our UAVs to capture data. So there are, because it violates geo-privacy, which is very important in terms of responsible AI. So on the one hand, we have quite a lot of important applications in for example, urban areas. On the other hand, we cannot use our UAVs to capture data sets from these places, most of the time. Here you can see some of the UAVs that we designed from scratch at Helmholtz, which can capture data, multi-sensor data. So, but what if we can produce synthetic data? Or what if we can produce any types of data with any semantics without the use of any sensors? This shapes the backbone of image generation from text. So in image generation from text, all you have are some specific semantics in mind, and you try to produce images from these semantics. So the objective here is to generate realistic images without the use of drones. So we don't use any drones, but we try to produce hopefully realistic images through some semantics that we have in mind. Any semantics, like many pieces of farmlands are together, for example, or something like this. Well, when we started this work, DALI, later known as DALI version 1, was out. But in order to train that network, people used 250 million pairs of text and images to train a giant network with 12 billion parameters. But this wasn't the case back then in the remote sensing community. We didn't have such many pairs of images and text together. All we had was 8,700 images and text pairs to be used to train a network. So this is a big challenge. For that, we developed this method. Well, I'll describe that in a very abstract way, but of course, more information can be found in the corresponding paper. So the input that you have here are text description and input images. You pass them through two encoders, the image encoder and the text encoder. And as the output, you get text tokens and image tokens. And then you pass it through embedding layers and positional encoding. Why we use positional encoding here? Because transformers are different from sequential models. In sequential models like RNN or LSTM or something, you automatically consider sequential information, the contextual information, what happens next and what happens before. This is not the case for transformers. In transformers, you split the input data into a couple of chunks and you process each of those individually. So in order to give them a bit of context, you add positional encoding, which simply gives some contextual labels to different chunks. Well, after that, we concatenate text embeddings and image embeddings, and we pass them through n blocks of prototype learning, which I consider that as the main contribution of this work. Each prototype learning block is composed of one whole field layer and one self-attention layer. Well, as I mentioned before, the most critical problem that we have here is the lack of label data. So we need to come up with some sort of course to find learning phase, learning process. Something that we can, for example, learn the most representative features, prototypes, using very few samples. And this is what we are doing using prototype learning blocks. In prototype learning blocks, we use whole field layer and self-attention layer. One of those is an associative memory layer. So it memorizes the most important features in our network. And the self-attention layer can model the global contextual information. Actually, when we talk about whole field layer and self-attention layer, they have similarities with RNN or LSTM and convolutional neural network that we have been using for quite some time in the remote sensing community. CNN can model the contextual information, and RNN gives a bit of memory, not RNN, LSTM gives a bit of memory to these sequential information. And with that, you can hopefully emphasize on the most representative features. Well, we perform softmax and we get the predicted image token, and the whole network will be optimized by reducing the cross entropy loss between the probability vector of the image tokens and predicted image tokens. And the output of predicted image tokens will pass through decoders to produce the generated image. Well, this is a training phase, right? In training phase, we have both text description and input images. But when it comes to test phases, we only have text description. So we use only the text description to produce hopefully realistic images autoregressively. One good thing about this network is that it's parameter efficient as well. So one of the key problems that we have with deep learning is that we need to train quite a lot of trainable parameters. It's not environmentally friendly, actually, because it consumes quite a lot of carbon energy. Here, all the parameters in the encoder and decoder are frozen. How we can do that using, for example, autoencoders, or in this case, VQ VAE, which is very much similar to autoencoders. It uses encoders and decoders, but it also trains the code book or dictionary. And as soon as you train that and you minimize the reconstruction loss between original image and the reconstructed image, you can freeze the network, encoder and decoder, and you can use it in this, network. And with that, you freeze the parameters and you don't train them any further. Well, so some more information about whole field layers and self-attention layers. The good thing about whole field layers is that they are differentiable, so they can be embedded in any deep learning networks, and they can contribute to the back propagation. I don't go through all those notations that we have here, W lookup and W content are two trainable matrices here. And with whole field networks, we can memorize the most representative prototypes or features, and we can use them to reconstruct realistic images whenever we want. And as I said before, self-attention is used to model the contextual information here. Okay. For the experimental part, we use this dataset. This was originally developed for image captioning. In image captioning, you have images and you try to produce some text information from those images. But what we are planning to do here is the other way around. So we only use text information, and with that we want to produce hopefully realistic images. The number of training and test samples are also mentioned here. 8,700 images for training and 2,000 images for the test part. And here you can see some of the results. Some semantics, and those images are fake. Well, again, responsible AI requires, one of the key components of that is to come up with one criteria or multiple criteria to evaluate the performance of the network. For example, overall accuracy is not the case here. You cannot use that. And there are some metrics available in the computer vision community, like inception score, but this really doesn't work in the remote sensing community. In remote sensing, most of the time you synthesize data or you produce data for the downstream task that you have, for example, classification. So here we proposed zero-shot classification overall accuracy as a metric. So here we use the text information, we produce fake images, and then we use the fake images to train our network. And then we perform the network on the test images that we have. Since we only train the network based on fake images, synthesized images, the accuracy that we get here for test images can really evaluate the results. And here, our approach could outperform other techniques, GAN-based techniques and transformer-based techniques in terms of zero-shot classification overall accuracy. And here you can see some results for some ablation studies for different hyperparameters that we use, number of, for example, prototypes, size of the embedding layers, and the shape of the prototype learning, and so on. So the considerations here, well, through producing synthesized images, you can address many problems that for which you cannot capture data, or for which you cannot produce data for a specific semantics. It can solve a lot of issues at the same time, but there are a couple of things that you need to consider. First, if you use, for example, synthesized data, it should be clearly mentioned in the paper. And when it comes to remote sensing, we cannot use only synthesized data. We need to have a good amount of real data to both train and evaluate the results as well. But all in all, we should be transparent to the methodology that we develop as well. For example, our methodology is not capable of handling different types of different colors. And this is one of the shortcomings that we need to mention, for example, in our documentations. Well, anyway, so all the things related to this work can be found in this link. Well, the third example, I call it community engagement, transparency, and fairness through open science and benchmarking, which can be attributed to ethical concerns. Well, for ethical concerns, we mentioned quite a lot of details here, including honesty, transparency, fairness, and something. But here I would like to emphasize more on the open science part of the responsible AI. Well, when we do something, and if it doesn't endanger, for example, some geo-privacy or some specific species, as is mentioned in the FAIR principles, we need to disclose our data set and the codes that we developed for that. And this is so in simple words, we should make our works as open as possible and as close as necessary. So as long as it doesn't endanger any, for example, geo-privacy, or for example, it was mentioned, endangered species or something, we should be able to disclose our data set. And this is really important. For example, I had a discussion with one of your colleagues a couple of days ago, and she said we don't have any hyperspectral benchmark data set in the community. Well, a bit of history about what happened in the remote sensing community. Until 2018, we didn't have that much of benchmark data sets, and this is why a lot of people use Indian Pines, Pavia University, or Salinas in their papers. I don't have anything against that, but when you use those data sets as the input to deep learning-based approaches, your training part and test part have overlaps, and you cannot really train your network in a fair way. So until 2018, we didn't have too many benchmark data sets. Since 2018, the community started to disclose more and more benchmark data sets. For example, through some competitions in 2020 and 2021, we disclosed some data sets, some larger scale data sets. And in 2022, for example, we organized another competition on landslide for sense, on detecting landslides on global basis. And we also disclosed many other data sets which will be introduced later in the next session. For example, MineSCD related to some mining activities on the global basis, and the first data set on AI security. But again, until 2018, we didn't have too many benchmark data sets. Since 2018, the community started working and disclosing benchmark data sets. And it was around 2020 that we pointed out, we have so many benchmark data sets, but we are somehow losing the track of available data sets because all of those are stored in private repositories. This is why we submitted a proposal to IEEE GRSS, and we got the funding to produce Earth Observation Database, or EOD. So the objective here is to provide an exhaustive list of available data sets with their basic information, which can be accessed and extended by the community and queried in a structured and interactive manner. Actually, there are a few nice things about this database. First of all, you can easily go there. You can add your data set there. And since you simply provide a URL, the address of your available data set, you will always be the data owners, and you get all the credits for that. And you can also advertise for your data set here. So you can simply go there and add your data set there. And this is a database using which the whole community can understand, okay, these data sets are available. So this is for adding your data set there. In addition, you can find some data sets with respect to different criteria. For example, with respect to tasks, for example, scene classification, semantic segmentation, fusion, and something. With respect to the sensor type, SAR, hyperspectral, multispectral, and so on. And with respect to geolocations, if this option still exists, I don't remember that. But, so you as a data owner will have all the credits there. And IADF, which manages this data set, doesn't receive any credit for that. And today, I think we have more than 200 larger scale data sets there. Okay. So, the EOD, Earth Observation Database, designed by the IADF TC, actually balances the advantages of open science and privacy concerns through case-by-case evaluation. So you add your data set. In the back end, IADF sees that, okay, this data set can be added to the database or not. And with that, you promote open science, and at the same time, the IADF can see that whether these data sets are against geo-privacy or not. And this is exactly aligned with the FAIR principles, as open as possible and as close as necessary. Well, any questions? Sir? Well, not in my age, but EOD is now managed by IADF. Maybe they, for example, I don't know, rejected some data sets there. I don't know. But in our time, no. All the images which have been added there were completely aligned with FAIR principles as well, so we added them all to the database. Sure. Sorry? No, you can, well, this database is only for reporting your data set, right? So as soon as you put your data set, for example, in your private repository, you can post it there as well. So some basic information about the size of the data, about, for example, address to your private repository, for example, and so on. No, there are not any rules for that. But hopefully in this community, we can come up with some rules. For example, the use of Indian Pines and Pavia University, for example. These small subsets of data are not appropriate for example, deep learning approaches. For now, we don't have any principles with respect to the use of the data set, but hopefully we can come up with something in the future. Any questions? No? Okay. So, what can we expect in the next session? So far, I provided you with one example about ethical concerns, geo-privacy, and mitigating biases. So 2 building blocks are left, AI security and social good. And we talk about these building blocks in the next session. And we also provide you with quite a lot of hands-on practices about all of those, not all of those, but about social good, AI security, and geo-privacy in the next session. So in more detail, for the secure AI part, we talk about adversarial defense. There are a couple of parts in secure AI, including adversarial defense, backdoor defense, federated learning, uncertainty, explainability, and so on. But here we focus more on adversarial defense for the AI security part. For the social good part, we emphasize on mining activities as the application. So this figure actually shows the whole story in a very nice way. It shows that as time goes by, the demand for raw materials is exponentially increasing. At the same time, some concepts like recycling or circular economy cannot generate sufficient supply for the text that we have in mind. So we need to still stick to mining activities, but how can we make them sustainable? How can we reduce the harmful effects of mining activities on the surrounding areas? This is something that we focus on that. So the objective here is to increase the acceptance of mining activities on a global basis by reducing the harmful effects of mining activities on the surrounding environment and improving the efficiency of that. So during the hands-on work, we introduced a large-scale, globally distributed data sets, bitemporal data set, to perform change detection, changes which occurred by mining activities. And also, we show you how you can produce automatic text description from bitemporal images. So this is change captioning, computer vision. So in more detail, we will provide you with MyNet CD and one platform named Unified Change Detection, in which you can find 19 change detection approaches together with a lot of pre-trained networks. And for the change captioning, where you want to produce automatic reports from the change areas, we also introduce this methodology, which you can see, for example, these are the images, and the text information that we produce here is, for example, a large building is built beside the road, for example. Okay, so far I talked about some of those examples, but what would be the next generation in the remote sensing community, and in particular in AI for EO? Well, when it comes to AI, it's really difficult to anticipate the next hypes, but in my opinion, one of the things that we will see a lot in the future is foundation models, or one model to rule them all. When I started my work in the remote sensing community 10, 12 years ago, I always had a dream to develop something which would be applicable to a variety of tasks. And this is exactly what we do with foundation models. Not exactly, it's a step toward that, yeah. So in foundation models, we bring together innovations in AI and data together, and we develop something sophisticated to be trained over millions of images. And with that, hopefully we can come up with something which would be applicable to a variety of applications. For example, here we developed a spectral GPT trained over 1 million or a bit more images, and it was applicable to a variety of vision-related applications like multi-class classification, single-class classification, change detection, and segmentation. And another research direction is prompter-efficient models, because in my opinion, the main issue associated with deep learning-based approaches are not overfitting or vanishing gradient or optimization degradation and so on. The main issue associated with deep learning-based approaches are the amount of carbon energy they consume. And they are not, and these giant networks are not environmentally friendly. So as a next step, we need to produce more or less similar results with much fewer parameters. For example, here for vision question answering, we got 1% better results with just 8% of the parameters. And I think one thing which will stay with us as long as science existing is open science and benchmarking, something which has been promoted by IADF in the best way possible. And I would like to take the opportunity, and I appreciate IADF for example, developing a lot of benchmark data sets, for organizing this summer school, and a lot of other things. What you are doing is exactly aligned with responsible AI. And the very interesting thing here is that all these people, Gulsen, Sylvia, I don't know, Roni, Claudio, and Fabio, for example, they are all busy people. But they do that free of charge and only for the community, for you. I would like to appreciate you all. Yeah.